Hello everyone, today we're going to solve some problems in stereochemistry. This will help you better understand how to use stereochemical principles to solve some organic chemistry problems. In this problem set, there are 4 pairs that are given, and your task is to identify whether they are constitutional or stereoisomers between the 2 pairs. So this would give you fundamental understanding of different type of isomers. When you come to the first problem set A, you have a compound with C4H80O and C4H8O chemical formula. That means they are chemical formula wise, they are the same. But if you closely see the structure, this is a cyclic ether. It's called, the functional group is ether. And if you see this compound right here, they are differently constituted from this one. This is a ketone functional group. So if you remember, functional groups are 2 different kind of chemical groups that have different chemical properties and physical properties. Therefore, even though they are chemical formula wise the same, they have different functional groups. Therefore, this pair is constitutional isomer. Their only common feature is that they have the same molecular formula. So when you go to B, you have a cyclohexane ring that's doubly substituted. That's metal group and metal group with a formula of C8H16. This is also C8H16. So they have the same chemical formula. And let's see how they are also constituted in terms of bonding. So there is a carbon-carbon bond, there is a carbon-carbon bond, the rest is the same. So in order to make sure that you have similar kind of comparison, you ought to change this into the flat cyclohexane form, which I would just change it into this form. So if you just look at this is axial, and that should be on top of the ring, CH3. This CH3 is also pointing that way. That means it is above the plane of the cyclohexane ring. Therefore, it also is CH3 on top. So if you just look at these 2, constitutionally they are the same. That means C8H16. Even the bonding pattern is exactly the same. But as you see, there are some differences how they are oriented in space. Therefore, these 2 qualify as stereoisomers. Stereoisomers. Let's pass to compound pair in C. You have C7H14 molecule. C7H14, they are the same in terms of chemical formula, but however, their constituents are made differently. Here the 2 metal groups are substituted on the same carbon. Here the bonding is 1 metal group is attached to carbon 1, the other CH3 is attached to carbon 3. So this is a 1,3 dimetal, but this is a 1,1 dimetal. So the naming even is different. 1,1 dimetal cyclopentane. But for this one, it is 1,3 dimetal cyclopentane. Therefore, in terms of their constituency, how they are made, how bonds are connected, the order of connectivity is different. this compound pair is constitutional isomers. Let's pass to the pair on D. If you just look at D, this is C8H16, C8H16. The bonding pattern looks like the same. You have dimethyl, you have a carbon-carbon double bond within the ring. Everything sequentially are the same. This is C8H16. So these two are actually, if you just do a flip, if you just flip the whole molecule and bring it like this actually, two of them are just the same molecule. It is the same molecule with one stereogenic center. We'll discuss this in the future, but this is the same molecule. If you just bring the whole molecule and rotate it to the right, it will give you just that. They are not mirror images, be careful. These are same molecule. So with this introductory problems we have, we'll go deep into the rest of stereochemical problems in the next section. Okay, let's continue our discussion on identifying what kind of relationships are existing in this pair of compounds. You see, we have A, B, C, and D. So if we start from the first one, these two pairs looks like they have C7H14 molecular formula, which are constituted very differently, meaning that this is a cycloheptane compound, but this is a cyclopentane, but doubly substituted. So the only similarities they have is they are both C7H14, but they are not constituted in the same way. So for this one, it's very easy to just assign that their isomerism will be constitutional isomerism. They are constitutional isomers because they have the same C7H14 molecular formula, but the substitution, how each carbon-carbon bond is made or connected are different. Therefore, they are constitutional isomers. When we come to this, there is more than discussion of the molecular formula. The molecular formula should be the same because this is a cyclohexane ring. They're substituted by dihydroxy OH. It has OH. But here, if you just look at this OH is in this molecule, it is equatorial. And this one is equatorial as well. And this one, it is also equatorial. And this one, it is axial. So how are they related? So the first question I will be asking you is, does this molecule, any one of this molecule, contain a stereogenic center? This is a very important question, where a carbon that is substituted to 4 different groups is called a stereocenter. So in the first glance, you might think that this carbon is a stereogenic center, and this carbon might be a stereogenic center. But be careful. In this case, this carbon is not a stereogenic center. That means the reason being it has the same substituent and this substituents are the same. At least this far out, this and this are different, but this and this are the same. If you just continue looking at this and this are the same, and they share both of them this carbon. Therefore, there are no 4 different substituents. there are only two different substituents. This and this are different substituents on this carbon. Otherwise, the two substituents are the same as symmetrically as you go. So there is no stereogenic center for this carbon. Be careful. Similarly, for this carbon, it looks like you have four different substituents, but the two substituents are symmetrical. They are the same. So if you just go out here, the substituent and the substituent are the same for this carbon. This and this are the same. Therefore, this is not also a stereogenic center. Therefore, this compound doesn't have any stereogenic center. If you also just check this one as far as stereogenic center, this is not stereogenic center, this is not, because if you just look at for this carbon, you have this and this are different, but the next two substituents, we put it as two substituents, this and this are the same, this and this are. So if any carbon has two same substituents on it, it's already automatically, it doesn't have a stereogenic center. So as far as any stereo center, they don't have. They have the same molecular formula. Let's just draw also how they look like in terms of a flat cyclohexane ring. Let me draw this one first. So in the cyclohexane ring, they are at 1 and 4 positions are the substituent. So for this one, the OH is down at this position. So if this is 1, I consider the other 4 would be there. So the OH is down, that means OH down. But here, OH is on top of the plane. This is pointing down, this is pointing up. Therefore, the fourth position, 1, 2, 3, at carbon number 4, it is up, OH. This is for this one. How about this one? How does it look like? For this one, just draw the red one. Okay, the OH is up. That means up. Axial. Equatorial, which is also pointing up into on top of the plane of the board or the cyclohexane chair. So this is also up. We draw it as OH. So if you just look at this, there is no any relationship in terms of what they look like. This is the cis. They have some geometric isomerism. This is a new concept. So this, because both OHs are in the same direction, this is a cis on the same direction. This is trans, because they are opposite. The hydroxys are, one is trans, down and up. Here both are up, so they are cis and trans. Such kind of isomerism is called geometric isomerism. This is called geometric. Cis and trans is, there is no stereoisomerism between the two because there is no chiral center. So this is geometric isomerism. Trans and cis. They are just trans and cis. No chiral center. Important. In both of them there is no stereoisomerism. Therefore they are just geometric isomers. They are trans and cis. These are trans and cis cyclohexane compounds. Okay, passing into the C, part C, you have a cyclopropane, which is methyl and chloro substituted. Here also methyl and chloro substituted. So you have to always be careful. The stereogenic center, this compound obviously has a stereogenic center. because this carbon is substituted with chlorine. Obviously, you should understand that there is a hydrogen sticking out on this, and you have one group here, hydrogen, and the fourth one is this. So you have chlorine, hydrogen, the third group, and this. So this is a stereogenic center. This is also a stereogenic center. So this compound is actually has two stereogenic centers. Obviously, on this one, you have this whole thing, and hydrogen here is into the plane of the board. So this is a stereogenic center, and this is a stereogenic center. But how are they related? Even without knowing assignment of R and S, we are not doing that now. I will just rotate this molecule, the top. Rotate top molecule to the right. So you just rotate it to the right side, hold this and rotate the whole thing. You'll end up the same thing. You are not lifting it, you are not turning it, just rotation would give you this. So you have to rotate this in a way. The rotation should be like this. So when you rotate it like this, it would give you, I'm just rotating it that way. So this will be Cl, this will be this. This would come here, that would go here. So that's what happened. So if you just look at these two, now this is the top one, when you didn't do anything, just the rotation would give, compare it to this one. When you compare this to this, if you just have a mirror and draw this, right, as it is, right, just bring and redraw that. You will just look at them, and they are mirror images. These are mirror images. So therefore they are stereoisomers. Isomers. Specifically, they are enantiomers. So remember what we have done. We didn't do anything. We just identified this. There are the stereogenic centers. So what I did is just rotate top molecule. So when you rotate it to the right, to the left, like this, you will end up with this. Rotate top molecule left. End up with this one. So this is top molecule. This is the molecule down. So if you just look at them, their relationship is just mirror images. Okay, let's pass to the last molecule, which is D. If you just look at them, on this one, the way you would be able to identify what kind of relationship they have is just to assign the R and S of this. So priority-wise, for example, in the first molecule, priority-wise, this is priority 1. This is priority, no, that's not true. This is priority 2. Iodine is priority 1. Chlorine is priority 3. Hydrogen is priority 4. So this is how it looks like. In this also, priority 1. This is priority 2. This is priority 3. This is priority 4. So the way I will just put the hydrogen back into the plane of the board would be by rotating it this way. For example, hydrogen would go into the plane of the board. Okay, but this would come like this. So this would be chlorine, right? So iodine would be here, right? And bromine would be here. But remember, hydrogen is already moved inside to the plane of the board. So this is 1 and this is 2. So when we just rotate this is clockwise. This is our R configuration. So that would be R configuration. How about for this one? For this one, okay, let's just have hydrogen now into the plane of the board. So the iodine would be replacing here. So I'm rotating it to the left. So if you just keep chlorine here, iodine is replacing hydrogen. Iodine. And now the bromine would come out here because we are rotating this. So the hydrogen is the fourth priority is into the plane of the board. This is going to that. So this is an S. So the two molecules are related as enantiomeric pair. R and S, mirror images with one stereogenic center. This is a stereogenic center. I will mark this as a stereogenic center and push down hydrogen, the least priority atom, to the plane of the board, which would give you R and S. So those are mirror images. Specifically mirror images, and with one stereocenter. They are stereoisomers. Specifically, they are enantiomers. So this is how you would be just trying to figure out what the stereochemical relationship between different compounds. So in the next one, we'll do more exercises how to assign R and S, how to assign. Okay, we'll continue our discussion on chirality. So I have A, B, C, and D molecules just to discuss about chirality. Chirality is when a compound has a stereogenic center and it's as active for against plane polarized light. We call that molecule a chiral compound. So if you start with A, if you just look at A, the chiral center could be, potentially this is what the chiral center will be examining. So that's carbon. It has group 1, which is CH2OH, CH3. This is actually hydrogen, let's say. And you have CH3, another CH3. This compound cannot be a chiral compound because that carbon has 2 identical substituents on it. So for a compound to be a chiral center, it should have 4 different substituents around the carbon. So this is a carbon we are dealing with. This is CH3. This is another CH3. This is H. This is CH2OH. But this compound has 2 identical substituents on it. That doesn't qualify as a chiral center. Therefore, this compound is achiral. No stereogenic center, it is achiral. it's not active in plane polarized light. It doesn't turn plane polarized light, and it doesn't have any stereoisomerism. It doesn't have any stereoisomer because it doesn't have a chiral center. So if you also deeply look into this compound, if you just put this H2OH and hydrogen on the same plane, in flat plane, this would be crossing. For example, if you have this mirror plane, if that's a plane cutting horizontally, that holding hydrogen and OH, CH2OH, the two are mirror images. So a compound which has a mirror image within itself is also achiral. So a plane of symmetry within a molecule makes the compound achiral. So two definitions. Compound is achiral if it is substituted by two identical groups, and definitely it would have a plane of symmetry like this, which reflects this to this. So each one is reflected to itself when you cut it. So there is a plane of symmetry which makes it achiral. So this compound is superimposable on its mirror image. So achiral, or on its superimposable on its mirror image. But if it was a chiral compound, and if it's enantiomeric or diastereomeric, you cannot superimpose it on its mirror image, but this one does. Okay, let's see the next molecule. This molecule, if you just consider that carbon, it has hydrogen, group 1, amine group, NH2, group 2, another group which is different, 3, that's the acid functional group actually, and this whole group is another group. So it has 4 different substituents on it. So that kind of molecule qualifies as a chiral molecule. So this is an amino acid actually, so it's chiral. That means it rotates the plane polarized light. It has a stereogenic center. Usually I mark stereogenic center with that carbon, and it's chiral. So if you write this and its mirror image, for example, if I just does a mirror image of that, it would be COOH, and this is this NH2, this is hydrogen, and that is CH2SH. So this is a mirror image one another. So this is chiral, therefore its mirror image is also a chiral molecule. So in the meantime, I also want to go through how you assign whether this compound is an R or an S molecule. We can just do by assigning priority. So this carbon is attached to nitrogen. So nitrogen is atomic number 14. Carbon directly attaches atomic number 12. This is carbon directly attached to this is atomic number 12. Therefore, the priority would be assigned for this molecule to be, one would be NH2, 2 would be this one. This carbon is connected to this sulfur, but this carbon is attached to oxygen. So between carbon and oxygen, this is priority number 2 because sulfur is more priority than carbon oxygen. This is carbon sulfur. This is carbon oxygen. So this is priority number 2, this is priority number 3. Since hydrogen is already at the back, we don't have to do anything. We can just move from 1 to 2 in a clockwise direction. Therefore, this is an R configuration of enantiomer R. This should definitely be an S, so let's work on it. So this is 1, this is 2, this is 3. Hydrogen is already on the back of the molecule, so this movement would be counterclockwise. This is an S configuration. So this compound is a chiral molecule. Its mirror image is also a chiral molecule. This has R configuration. This mirror image is S configuration. But if you just take and want to superimpose on one over the other, these are non-superimposable. You cannot adjust each one of them atom in the groups one over the other. So enantiomeric compounds are non-superimposable. Okay, so I hope you got this clear, and let's go to this molecule. This molecule is, again, it's similar to what I have already. So this actually is the same molecule to that, but as you see, there are two similar substituents. So this is a chiral, so no stereogenic center. So let's continue working on the next molecule. This is the next molecule we have, and let's see what the mirror image looks like if I just draw a mirror image, because there is a chiral center right here, because group 1, one group, another group, 4 different groups. So this is a chiral molecule, and its mirror image should be also a chiral molecule. So let me just draw its mirror image, CHO, and this should be H right there is the mirror image. The mirror image of this is OH right here, and CH3 right there. So these are mirror images, and I expect them to be chiral, which is true. So this is chiral, and let me assign the R and S for this molecule. This molecule is priority 1 is this group, priority 2 would be this group, because this CHO is actually attached like this, COH, so carbon oxygen than carbon hydrogen. So the priority would be 2. This is number 3. Here hydrogen is number 4. So the lowest group, which is hydrogen, is in front of us, but we want to push hydrogen to assign R and S. We always push the least prior atom to the back. So if I just rotate it to the right, I will draw this COH. This is just rotation. So if I rotate this way, so that this would go back, and the OH comes here. So the OH comes here, and the CH3 replaces this. So CH3 would be here. So it is 1 here, this is 2 here, 3 is here. Now hydrogen is to the back, so we can easily move from 1 to 2. The rotation is clockwise, therefore this is an R configuration. So this is R configuration. That carbon is R stereocenter. How about this one right here? So assignment priority is 1. Priority, let me redraw this. This is actually this. That's why it's 2 priority. This is priority 3. This is priority 4. So redrawing this by pushing hydrogen to the back, by rotating it to the left would give me COH. So rotating to this direction would give me CH3 where hydrogen was, and OH where CH3 was. So this is 1 and this is 2. So now the rotation is toward this. This movement is an S, which is consistent with what I have. This is an S configuration. So I want you to practice how to assign priorities, how to push the least prior atom to the back of the plane of the board and assign the R and S. And remember also, whenever you have a molecule that has no 4 different substituents but rather 2 similar substituents, that's a chiral. So there is no way you would assign as R and S, so it's superimposable. So this does not have any optical activity, rather you would have optical activity for R and S or diastereomeric compounds. Let's continue our discussion on stereoisomerism. Now our problem here says how are they related. You have compounds A, B, C, D, 4 compounds with molecular formula of C3H6O2. So all of them have the same molecular formula and they have also the same kind of bond connectivity. Therefore this compound is mostly should be stereoisomers, but we want to know exactly how they are related. Some of them might be the same, some of them might be mirror images, that means enantiomers, some might not be even not related, or they might be the same. So let me start by solving the R and S assignment of this molecule, starting from here. For A, the way how to draw this would be to assign the R and S is to push hydrogen to the back and CH3 to change here position by just rotating it to the right. So this is equivalent to CHO is here, CH3 would be here, and hydrogen is the back, and OH comes here. So now, remember, now hydrogen is to the back. This CHO is actually really drawn as aldehyde functional group. So this is priority number 1, this is priority number 2. So this is the stereogenic center. Remember, that's 4 groups that are attached to this central carbon. So this rotation would be clockwise. This is an R configuration for this compound. So this is an R enantiomer. So moving on B, this is of course the chiral center. You don't have to redraw anything because hydrogen is already to the back. This is actually like this. Sorry, so this is COH, that's aldehyde group, that's how you should draw it, and OH is like this. So this is a redraw of while hydrogen is at the back. So this is priority 1, this is priority 2, so this would be an S configuration, S enantiomer. So basically R, this is S, this is still C3H6O2. Now coming to this one, we are just looking at this molecule. Hydrogen is the back, so this redraw would give us CH3 OH. The aldehyde group is here, CHO is redrawn like this, and hydrogen is at the back, so there is nothing you can do for this, you just leave it as it is. So this is 1, this is 2, So this is a rotation like this. That is clockwise. That is R configuration. So you have R for this one. Here, when it comes here, you have to be kind of careful. The way it is drawn might be a little difficult to see, but what I will do is I will just push back the CHO group to be vertical, push it like that, so then the CH3 would come here. Okay, so the CHO would be there and CH3 would be here. So what I'll do is just rotate it on the plane of the board like this. You just turn it on to the left, so that CHO would come here, while CH3 would go this way out. Right, so the H is still towards me, and OH is like that. So remember what I did to this is just a little rotation towards this. Just bring it back to stand it up like that. So this is CHO can be drawn as, actually, to make it clear, that's an aldehyde drawn like this. Now, so the hydrogen has to go back. Okay, and this is priority 1, this is priority 2, this is priority 3, this is priority 4. So we cannot determine R and S while it is like this. So the way I will do this would be to bring CH3 to the left. That's just a rotation. It doesn't change the molecule. So it will replace the place of hydrogen. That means CH3 will come here while you're rotating it. Hydrogen, when it's rotated to the left, it should go to the plane of the board, and then the OH should come up and replace CH3. So that is OH here. So now hydrogen is obviously at the back. I'm just showing it for you to be clear. Now you have 1 here, 2 here, 3 here, 4 here. So now we are moving from 1 to 2, which is counterclockwise. That gives me S. So in this case, now A and B, the relationship when we find out at the end, A and C are same molecules, right? Same R molecule. So they are the same. So if you just take A and B, and A and B are enantiomers. A and D are also enantiomers. A and D are enantiomers, mirror images, right? So what is the relationship between B and D? B and D are same molecules. So basically we have A with C, A with B, A with D, and B with D. So B is S and D. And so also you can also say that C and D are enantiomers as well. C and D are enantiomers. So you can establish a lot of relationships, but this is how they are related when you see them as stereoisomers. So all of this are stereoisomers, and their particular relationship, A and C, are same molecule, are AB enantiomers, AD, BD, CD, and How about A and D? We have already established that. B and C, we can also establish B and C. B and C are enantiomers as well, so I will just add it here. B, C are enantiomers. So basically we have solved what the relationship is between all of this. These are stereoisomers, some are the same. For example, A and C are the same as we have already identified. So this is a way how you'd be just understanding the chiral center first. After you identify the chiral center, you need to just identify what kind of R or S configuration you have. After that, you can establish all the relationships that are possible for all the stereoisomers. So all of them are stereoisomers. Some are the same molecule, some are enantiomers, some are also the same molecule as already identified. So we'll still continue solving other problems. Let's also work on these problems. We have compound A, compound B. Our assignment is to assign the absolute configuration of all the stereogenic center. So when you look at A, the stereogenic center is this carbon, because it has one group, two group, three group, and the whole of this is one group. That is, this is an ethyl group, this is a chloro group, this is a hydrogen, and this whole substituent is one another group. So if we redraw this in a way that this is very clear to us, you have CH2, CH3, and this whole group, I will call this the whole group as X, that's X, and this group is hydrogen, and this group is chlorine the way it is. So in the priority assignment, chlorine is obviously number one, and next to that would be this X group is greater than all of those, because this is carbon, next to it is hydrogen, but this is carbon, next to it is another carbon and another chlorine. So priority wise, this would be 2. So X is priority 2, and this is priority 1, and priority 3 is this, and priority 4 is this. Since hydrogen is still towards us, we should try to push hydrogen to the back of the plane of the board, so that I can draw that by just rotating it to the left. This would give me CH2, CH3, and bringing X to this position. That is, this would be an X, which is priority 2. This ethyl group is priority 3, and the chlorine would be just replacing the X position. That is chlorine 1 position, and of course hydrogen is at the back, so we'll leave it as such over there. So now it's much easier to assign for this. So we are going from 1 to 2, so that position is R configuration. So assignment of that carbon right there is an R carbon. So I'll just put it here, redraw it again, CH2, CH3 with hydrogen, chlorine, and another chlorine, and ethyl group, and of course this hydrogen. So this is an R configuration. We assigned R for that one. Now, how about assigning for this stereocenter? this is a stereocenter as well, because this is one group chlorine, another group hydrogen, another ethyl group, and this whole group as a whole. So when I come here, let me try to assign for this. So now you have this group. If you just rotate the whole thing like this, so that this would be vertical, so this whole group, this is hydrogen the way it is, chlorine, CH2, CH3. I'm just turning it this way, so that vertical it was this, and now we are just bringing it like this. So this is this group, this is chlorine, this is hydrogen. I just turned it like vertical. So group 1 assignment would be this was 1. Obviously this is 2. The metal group here is 3. And 4 is hydrogen. So the hydrogen is already into the plane of the board, so I don't have to do anything for it. So this chiral center now is determined as rotating it to counterclockwise. So if you just see this is counterclockwise, that means it gives me an S configuration. So this is S. So this molecule is an R and an S. So my question to you would be, if there are mirror images also, this might qualify as a meso compound, because within itself there should be a plane of symmetry. So what's the plane of symmetry? So the plane of symmetry is, if you just rotate this and see if there is a plane of symmetry for this one, you would find there would be some plane of symmetry, because there is chlorine, there is chlorine. So this part of the molecule is reflected into this part of the molecule. So there is a plane of symmetry. So that molecule actually is equivalent to CH2, CH3. You have hydrogen, you have chlorine, you have now if I just turn the CH2, this is a single bond, you know, it should always can rotate. So if I just rotate while holding this like this, if you just turn the CH2, CH3 to up side, you'll end up having it here, and the hydrogen would come towards you, and the chlorine goes back like that on this carbon. So if you just look at that, this is a plane of symmetry. This is a mirror. Exactly. You are reflecting hydrogen to a hydrogen. Chlorine is reflected to chlorine. Ethyl is reflected to ethyl. So this molecule has a plane of symmetry within itself. So this is R, that is S from what we identified. Obviously R is reflected to S. Such molecule which has a plane of symmetry within a molecule, we have already defined such compound as meso compound. And I have already told you that a meso compound that is not active in plane polarized light. It doesn't turn plane polarized light. So overall, as a whole, the molecule is achiral. See, here is a situation where you have stereogenic center, but the stereogenic centers are mirrored to one another, with the molecule being meso. Overall, the compound is not turning plane polarized lights, therefore it's called achiral compound. So remember, this is R and S. Let's work on this one. It has the same constituents if you just look at this, but the configuration in space might be different from that one, and we want to identify how they are related. This molecule and this molecule, how are they related? So let's identify the R and S. Just as the weight is, we will determine the R and S. So here, if you just turn the whole thing to left, you will be drawing this. So you will be doing this, chlorine, hydrogen, and CH2, CH3, and on top you would have chlorine. So you are turning it like this, hydrogen, and ethyl group. So this is basically what I did, just turn it like this so that I can determine the stereogenic center here and here as well. So the stereogenic center right here and here are those. So now if you just look at this, this is chlorine, that's hydrogen. So priority 1, and this is priority 2. But this hydrogen is at the back, which is priority 4, priority 3. Therefore, I'm going from here to this, that's counterclockwise. Therefore, this right here is an S. So that's an S molecule, right, for that carbon. And if I determine the same thing for this one as well, so if you just look at this, and hydrogen is the back, I'm just looking it down there. So this is priority 1, this is priority 2, this is priority 3. So if I'm just looking at down there as the tip of the molecule, hydrogen is the back, so I'm going from 1 to 2. So this is also an S. So this is also an S configuration. So if this is RS, but this is SS, the relationship between these two is diastereomeric. R, S, and SS, they are diastereomeric. Diastereomeric. So, can you draw any plane of symmetry in this? That's impossible, because S cannot be R here. It's already an absolute configuration S. So there is no plane of symmetry for this one. This one does not have plane of symmetry. So we have identified several things here. The relationship between these two. This is obviously we have identified it as R and S. SS is not a mirror image to that. So those are stereocenters where you have a diastereomeric relationship. If they were enantiomers, RS and it would be SR. But these are not enantiomeric relationship. These are SS and RS, and they are diastereomeric compound, while the top has a plane of symmetry and becomes a meso compound. This one does not have a plane of symmetry. Therefore, this molecule as a whole is also chiral. Doesn't have plane of symmetry, qualifies it as chiral. Therefore, this gives a positive or a negative plane polarized light. It can rotate a plane polarized light. So these are all the properties of this compound. It doesn't have plane of symmetry, it is chiral, and it rotates plane polarized light. So with this, we'll also continue to identify more stereogenic centers and different properties of stereochemically distinct molecules.